Okay, let's continue. So in the last class we looked at how we might go about sizing transistors in practice. That is a lookup table based approach. So I'll send out some basic, you can now practice your own design problems. You can try to do the same thing we did. I'll maybe post some more like design practice for you to do it. Details regarding simulators will be uploaded. So how many of you already have access to that VirtualBox setup of Cadence? So, or maybe how many of you don't have? Okay, document will be sent out, so you guys can do it. Okay, cool. So yeah, so to give a broad recap, so far in this course we did the following. Our goal was to design an amplifier or op-amp that has a very large gain. So we started with this simplistic structure, then we converted it to a differential structure like this, and here the gain depends on the GM of the transistor and the RD. Now to increase the gain, we wanted to increase RD, and ideally we would want this to be an open circuit in small signals. So you want this to be what? Yeah, ideally what would you want to put here? A current source. Incrementally it should be open. So that's what we did. We replaced it with a current source, which was a PMOS transistor, and then we made the differential version, and finally to generate the bias voltage for the current source, we did this self-biasing here, right? And here if I label the transistors, say M1, M2, M3 and M4, the short circuit GM here is coming from which transistor? Which transistor is contributing to the short circuit GM? M1 and M2, right? That is the main differential pair that converts the voltage to current. And what is the output resistance here? R0 of this fellow, R04 parallel with R02. But again, please remember, it is not as though looking down the resistance is R0 of 2 and looking up it is R0 of M4. We in fact calculated it separately, but the final expression turns out to be this. Okay. So now you see that the gain with this structure is of the order of GM times R0. That's what you essentially get. And from the last class, from the example plots I showed you, you can see the gain is of the order of few hundreds maybe. For that too for a very long channel transistor, you can get, let us say, a few hundreds. But in practice, you might want gain more than a million or so sometimes. So which means we need to do something to make this better. So let's see what we can do. So again, what we'll do is we'll start from this structure. We'll try to increase the DC gain of this single-ended structure, because once we know how to make it, it's a piece of cake for us to go from one to next. Okay. So again, so let me start like this. The motivation for having a PMOS transistor here was to realize a current source, correct? That's what we wanted to have. So we decided to have a PMOS transistor like this. I'm drawing the small signal picture. So this is the current source, and you had the main transistor here, right? So now we know that this is not an ideal current source. It has some output resistance R0. So that's what limits the gain. So if you want to make this a better current source, what is a suggestion? I have a current source. I want to make this to a better current source. So what can we do? Yeah, increasing R0 is another way of saying the same thing, but how can you make this a better current source? You can put a current controlled current source. That is, you take this current, give it to a current buffer, and current buffer is this common gate. This is essentially cascode, and let's say you try to do this. So let me label this as M2, M6 and M8 maybe. So what is the small signal gain here? What is the short circuit GM here? What is the short circuit GM? You should be careful, it is minus GM2 because you short circuited and find the current. You find the current this way. So it is minus GM2, you have an inversion. And what is the output resistance? So you have two components. What is the output resistance looking up?
GM6 R06 R0.
It is the cascode impedance. It is GM6 R06 times R08. Intrinsic gain of this fellow times the resistance of this. And what is the resistance looking down?
R02.
R0 of M2. This is fine. So what is this approximately then? How can you further approximate it as minus GM2 times what is this parallel combination approximately? R02, because this is much greater than this, so a smaller resistor is going to dominate. So well, I mean, looks like we did increase the output resistance here, but seems like we are back to square one. And why is that so? I mean, although increase the output resistance, it seems like the final gain is only GMR0. So what is limiting the gain here? I mean, looking up I increase the output resistance, but looking down it is still the same old R0. So what do you suggest we can do to increase the resistance looking down? We can put a cascode for the downside also, right? That's the only trick we know to increase the output resistance. So that's what I'll do. So let me redraw this. I have the PMOS current source. This is the PMOS cascode transistor. Now I want to make sure that the current from this guy is also mirrored by another current buffer. For the NMOS side also I'll have a cascode device like this, and then I connect it this way. Okay. So if I now label this as M2, M4, M6 and M8, and this is my output. So now what is the small signal gain here? What is the short circuit GM here? What is the short circuit transconductance here? That is, if I go and short circuit this, what is the short circuit current flowing? Can you check? Yeah, minus GM2 VA. Okay, be careful with the signs. So the short circuit transconductance is, shouldn't be so shocking because we didn't do anything to change the transconductance. Only the only thing we did was to increase the output resistance. So now what is the output resistance? Looking up, what is it? It is the cascode here, GM6 times R06 times R08. That is put in parallel with the impedance looking down. What is that? GM4 R04 times R02. Okay. So if I just were to assume that all GMs and R0s are equal, so this is of the order of, so I'll just take the magnitude of the gain. Don't want to play with the negative sign. So this is some GM times GM R0 times R, right? So this is of the order of, this is equal to GM R0. So this seems like one nice way to go and increase the output resistance and to increase the overall gain. So now we have made the single-ended version. So let's try to make it to a differential. So we have improved the DC gain of this structure. From here we'll go to the differential version and do this. So let's quickly draw that. So I'll have the PMOS current source at the top. Let me draw it a little bit more. This is the PMOS current source. Or let me not use too much of colors. I'll use the same color here. And then you have the PMOS cascode transistor, right? And then you have the NMOS cascode. And then the final transconductor, which is taking the voltage and converting it to the current. Okay. So let me label this, say M1, M2, M3, M4, 5, 6 and 7, 8. And again, just to make it clear, this is the PMOS current source. The top one is the main current source, remember. the bottom stack is the PMOS cascode, that is to boost the output resistance looking up. Now the next lower stack is the NMOS cascode, that is added to boost the output resistance looking down, and this is your final display. Okay. So again, all these have to be biased, so let's not worry about it for now. This fine? So if this is clear, I'll erase this to make space. Any doubt? Okay, so now let's try to quickly find the okay, now we are still not finished. So where did it go? So from here we have come back here, and finally the last job here to get this kind of circuit is to generate the bias voltage for the current source. So here the top one is the current source, so we need to generate the bias voltage. So let me mark all the bias voltages. Okay. And to jog your memory, in this circuit, the way we generated the voltage was this. We wanted to make sure the current flowing through the PMOS transistor equals the current in the NMOS transistor, and then we saw that if, let us say, the current in the PMOS transistor is greater than the NMOS current, what will happen to this voltage? You are pushing in more current into that node, so this will increase. Now as a corrective action, what should you do to the PMOS current? I mean, now right now the PMOS current is greater than the NMOS current. Your goal is to make them equal, so you need to decrease the PMOS current. For decreasing the PMOS current, what will you do to the gate voltage? You increase it. You have to increase it. This is something you want to do. This is something already happening. So it's all nature's play. So you go and connect it like this. Right? That's how you got this connection, just to remind you. Is this fine? So now let's try to do the same thing here. So now I know that I'll have current flowing in the NMOS side. Now the current from the PMOS transistor will be mirrored by this fellow. So my goal is to make these two currents equal. And for changing the PMOS current, which voltage I should change? VB 6 or VB 8 or VB 4? Here, which is the PMOS current source here? The top is the PMOS current source, remember. So if you want to change the current, what will you change? Clear? So again, can you tell me what do I do now? If this current is not equal to this current, same thing, this voltage changes. And yeah, it's the same thing. So you can essentially go and connect this. Take some space, hold on. This fine. And this is your view. Okay. So very comfortable with how we got this connection. Okay. The same thing we are trying to do here. So the idea is I want to make sure that the current flowing through the NMOS stack is equal to the current flowing in the current flowing in the PMOS is equal to the current flowing in the NMOS. Now we can argue the same way. If the PMOS current is greater, this voltage will keep increasing. Correct. Now as a corrective action, you are supposed to reduce the PMOS current. That will mean you have to go and increase the gate voltage here. So this is something you want. This is something that's already happening. So you just go and connect.
Can you argue for the two PMOS?
Which one?
For the two PMOS currents to same, we can argue the same thing.
I mean, you are saying for these two?
Yeah, like you argued for NMOS and PMOS.
Correct. Okay, exactly. So that was good. I thought if no one is asking the question, I will ask the question myself. So since he asked it, it saved me a few seconds of time. So this is something that will work. Fine. So what he is suggesting is this. So just like how I argued for here I argued for these two currents. Now I can do the same thing for the current flowing through M7 and M5, right? So which means I can generate the required bias voltage by doing this. Now I can extend the argument for the currents flowing through M5 and M3, and I can do this also. This is also something you can do to generate the bias voltage. Okay. Again, so both of them seem to be doing the same job of, both of them seem to be biasing the circuit, but we'll compare it towards the end of the class and see what is the pros and cons of each. Okay. Why do we connect it to M1? This one. But remember, this is where you're supposed to feed the input, right? V1, V2. You wanted to connect it to which one? Gate of M7 to? Okay, this way. This is also fine. You can think and see. Okay, now since you asked it, this will be an exercise problem. This is something I like. So we'll discuss it. Okay, but this is an interesting question. So I'll give it as an exercise problem. You think of it, we'll see. See, there are different ways in which to do it, right? So one advantage when you do this is, here you have to generate the bias voltage VB6 separately, but here you are basically doing it. So we'll see in detail. Okay, cool. So yeah, anytime you come up with some new circuit, the first job is to name this. So if you had come up with the circuit on your own, you could have put your name behind, but tough luck. So this is what people call as telescopic cascode, because apparently this looks like a telescope, or maybe it does. Okay, so now we'll consider the left side variant first and understand this, and then we'll come back to the right side variant. So let me copy paste this. So we'll do the same thing that we did for the 5 transistor OTA. This time we'll start with the small signal gain because it's easy. So again, this is a symmetric circuit or asymmetric circuit? Asymmetric. So to find the small signal gain, what is the approach we can take? What might be easier thing to do? You find the short circuit GM and R out. So I'll give it as an exercise, but what do you think the short circuit GM will be? Can you guess? If I short circuit this, which transistor do you think will contribute to GM? It's essentially this thing. Shouldn't be surprising again, because nothing is changed for GM, but you take it as an exercise and argue the same way we did for the 5 transistor OTA, so that you get used to these calculations. And similarly, R out, you find it as the up resistance in parallel to the down resistance. That is also an exercise. You find GM and the up and down resistance. But can you guess what the output resistance finally might be?
GM4, R04, R02, parallel GM6, R06.
Yeah. So again, you can follow the same logic. Here, although the looking up, looking down impedances were not trivial, the final result was nice to remember. This R0, the output resistance of the top side in parallel to the output resistance of the bottom side. So the same thing you can guess here. So it is the output resistance of the PMOS cascode, which is GM6 R06 times R08 in parallel to the bottom side portion, that is GM4 R04 times R02. But again, you can individually find what will be the up and down resistance. So that is an exercise. You can do the same thing we did for the 5 transistor OTA. Things will be very similar. Okay, so now that we know the small signal gain is fine, let's see how the operating point is set. So paste it again. So for the operating point, I have bias voltage here, I0 here, bias voltage up. So what do you think will be the currents in the 2 transistors, bias current? Yeah, why? Huh? VGS is? So
same argument, and most current will be directed. There will be contradiction.
Yeah, I mean the same thing we did for the 5 transistor OTA. This is again asymmetric. The current also depends on the VDS, by the way, right? So we have to see what will be these voltages. But once again, you can prove by contradiction that if you assume one drain voltage is greater than the other, you'll end up with a contradiction that PMOS up current is not equal to the down current and so on. So finally, the stable operating point is what? What will be the current? What will be the currents? So by extension, what can you say about, let's say I call this V3 and V4, or no, I'll call it VD3, VD4 to be clear. Drain voltage of M3 and drain voltage of M4. So what do you think VD3 and VD4? How do you think they will be related? They'll also be equal. So again, this is extending our earlier observation that although this is asymmetric, as long as you provide symmetric excitation, a common mode excitation, both sides will be symmetric. Okay. So these two voltages will be equal, VD3, VD4, and what will that be in turn equal to? What is determining this voltage? Remember that this drain is connected to the gate of this PMOS transistor, and the currents in the branch, both sides are equal to I0 by 2. So all transistors must have a particular VGS to sustain that current. So this is VDD minus source to gate of M7 or M8. So I'll just use M8. VSG of M8 at a current of I0 by 2. Right? Okay, so similarly, what can you say about the drain voltages of M1 and M2? Do you think they will be equal? Do you think they will be equal or not equal? They will be equal. Again, the same symmetry argument we can invoke. And what is determining these drain voltages? VGS of M3 and M4. Is that clear? Again, the same logic for, we know that the current is going to be I0 by 2. So which means the gate to source voltage is fixed. So this voltage will be VB4 minus the gate to source drop of M4. Okay. So this is VB4 minus VGS of M4. So I'll write that here. This VB4 minus VGS of M4 at a current of I0 by 2. Okay, so then only these voltages are pending, VD7, VD8. So these two voltages, they will also be equal, no surprise. And what will be determining the drain voltages here? Of the same argument as before. Again, the current in the PMOS transistor is fixed to be I0 by 2, which means the source to gate voltage of this fellow must be fixed. So VD8 will be VB6 minus the source to gate drop. Okay, so this is VSD6. So this will be VB6 minus source to gate of M6 at a current of I0 by 2. Oh yeah, sorry, thank you. Thanks. Good. Okay, cool. Fine, let me maybe copy this. Okay, so now we have we know that this DC operating point is fine, and we know that we get a good small signal gain. So what did we do next for the 5 transistor OTA? Yeah, I mean for the 5 transistor OTA, what all we found? Swing limits, right? Again, the same thing. We decided to put this fellow in negative feedback like this, but then we wanted to know what will be the range of voltages you can apply here, and this is indirectly computed by looking at 2 parameters for the OTA. And what are they? the input common mode range and the output swing limits. So let's quickly do that. Okay. So I'll erase this. I'll even know this feedback. I'll make some space. Okay. So now we are looking at the input common mode range. So both terminals see the same voltage, because we know when we put in negative feedback, the non-inverting and the inverting terminals of the op amps will be same. So we define that to be VICM. Okay, so now let's do that. Let me make some more space. Okay, now tell me, if I keep reducing the ICM and I'll replace the ideal current source with a transistor. This current is I0. This is M0. So if I keep reducing VICM, which transistor can go out of saturation? M0. This is same thing as we saw for the 5 transistor OTA, because VGS is fixed, because the current is fixed. Current is I0 by 2 because both sides the gate voltage is same. Okay. Again, as long as we provide symmetric excitations, things are symmetric. So current is fixed, which means the gate to source voltage is fixed. So if you reduce it, this fellow reduces, taking M0 out of saturation. So what is the lower end? I'll write it directly. So this is limited by M0. What is the minimum you can go then? Yeah, good. Again, you can directly write it. We know VICM is sum of these two voltages. This voltage is VGS of M1 plus VDS of M0. I know VGS is fixed because the currents are constant. So the lowest it can go will depend on how low VDS of M0 can go to. And the lowest the VDS of M0 can go is what? The overdrive of the transistor. So we should be able to write this directly now. This is VGS of, let us say, M2 at a current I0 by 2 plus the overdrive voltage of M0 at a current of I0. So let's try to write it directly without writing all these things. But is the explanation clear? Any confusions on how I got this? Okay.
So, a small doubt.
Yes.
Whenever you break V1 and V2 into VICM and VID, then that V1 and V2 include small signal, or is it just the bias voltage?
Yeah, I mean, the best way to understand this is like this. We are looking at when the OTA is used in negative feedback, because that is end application, right? So now you look at this, right? So this will be connected to some bias voltage. Here some other bias voltage plus a small signal VI. So in this particular configuration, what will be this voltage? So what is the common mode? No, what is VICM then? Common mode is essentially average of two quantities. Common mode is a fancy definition of the same. So what is the average of the two inputs? So here there is no small signal component. In this configuration, no, but let us say I put it in something like this, a unity feedback like this. So now what will be this voltage? VB plus. So what is VICM here? It is the average of these two voltages. It is the same. So here it does include. By VICM we are just saying the common input we can apply on both sides. Now whether that comprises of only the bias or also it includes the small signal component, it depends on the end application where the op amp is going to be used. Right? So that's why as a OTA designer, you don't have to worry about where it's going to be used finally. You just specify, hey, this is my op amp. At the input common mode, at the input, the minimum common mode can go so much, maximum is so much. Now the user can go and back calculate how much will be the range of VBVI based on the end circuit. Right? Okay. So this is the lower end. So now let's look at the upper side. So if I keep increasing VICM, which transistor can go out of saturation? Yeah, why?
Gate is increasing.
Gate is increasing, but what can you say about the drain? Why?
Because the current is same and it is being fixed.
Yeah, as he's pointing out, we know that if you increase the gate voltage for NMOS transistor, it is a recipe for things going out of saturation. And here the drain voltage is fixed to this value, right? This is the drain voltages. This is the drain voltage. It is VB4 minus VGS. The bias voltage you are not touching, and VGS is also fixed. So which means this can go out of saturation. So on the upper end, it is limited by M1 or M2. Fine. And what is the maximum the gate can go? One threshold above the drain voltage. So this is the drain voltage of M1 or M2 plus a threshold. I already know what is the drain voltage. So this voltage plus a threshold. Okay. So I'll directly write it. So I already know the drain voltage, that is VB4 minus VGS4. So VB4 minus VGS4 at a current of I0 by 2 plus a threshold voltage of M2. Okay. This is fine. Now once again, if you think about it, this bias voltage VB4 will have its own range of voltages you can do, right? At the minimum it can go to some voltage, maximum it can go to some voltage, so that things are all in saturation. So absolute maximum for VICM can be when VB4 is at its maximum. Right? This bias voltage is under your control. Whatever voltage you are connecting it to, minus VGS plus VTH will be the maximum VAC. Okay.
And VD4 is fixed, so VD4 also, like VD4 plus VT, it will go max, right?
Which one?
VD4 is fixed.
Correct.
And VD4 is in our control. So it could go max up till VD4 plus VT, right?
VD4, yeah, I mean that's what, I'm not looking at the range. I mean you can work out, yeah, correct. You can work out what is the maximum for this, right? So the input common mode range is 10. What is the other range I have to find? The output swings. So let's look at the output swings. So let me erase this. I think it's fine. So again, let's try to do it. If I keep reducing the out, which transistor can go out of saturation? The drain voltage here is reducing. For an NMOS voltage, if the drain voltage drops, it is a problem. So what is the lowest the drain voltage can go here? No, I mean, remember that the idea is the minimum the drain voltage can go is one threshold below the gate. That's all, correct? So here the gate voltage is VB4. The drain can drop one threshold lower than the gate voltage. That is the fundamental limit. Right? Let's do that. So it's VB4 minus VTH4. It's limited by M4. Similarly, if I keep increasing V out, which transistor can go out of saturation here now? M6, right? Because the drain of the PMOS is increasing, that can go out of saturation. So what is the maximum drain voltage can go in a PMOS? It's one threshold above the gate voltage of the PMOS. So gate voltage, as you know, is connected to VB6 plus, I'll say mod VTH of 6. So this is limited by M6. Right? So now let's find out what is the absolute minimum and maximum the output can go to. And the minimum is limited by VB4. So if you want to find the absolute minimum Vout can go, what should I find? The minimum of VB4. Fine. So let's do that. So again, let's try to reason it directly and write it. So I'm trying to find VB4. If it's not clear, I'll use some other color. I'll use this. So let us say it's VB4 minimum. So now tell me, if I keep reducing VB4, which transistor can go out of saturation? M? Yeah, why? Right. If you keep reducing this fellow, the VGS is fixed because the current is same. So this drops, this can go out of saturation, correct? So now we can try to write it directly. VB4 is essentially this VGS drop plus the VDS drop. Okay, so this is VGS4 plus VDS2 and VDS0. So if VB4 has to go to the minimum value, what should happen? So what is the minimum VB4 can go to then? It is minimum of the sum, fine. But which here is constant among the three? VGS is fixed. So the only leeway you have is with VDS 2 and 0. And what is the minimum VDS you can have? The overdrive voltage. So let's try to write it directly. So what is VB4 minimum then? It is VGS4, that is fixed, right? So that you can't change, at a current of I0 by 2, fine. Plus the minimum you can have here is what? Overdrive voltage of M2. And the minimum you can go here is overdrive of M0 at a current I0. Right? So now let's, we know the VB4 minimum, so let's put it here and try to find what you get. So VB4 minus VTH4 is the output minimum. So if I go and subtract VTH4, I'll put it here, VTH4, fine. So now you see you have VGS minus VTH of M4. What is that? The overdrive of M4. Okay. So this is V overdrive of M4 at a current I0 by 2 plus V overdrive of M2 at a current I0 by 2 plus V overdrive of M0 at a current I0. Again, we could directly have told it, reasoned out directly for Vout minimum like this. Ideally, you want the minimum Vout to be 0. Ideally, you want the output to go as low as 0. But that is not possible because we have to drop 3 VDS. One is the VDS of M4, which is the overdrive voltage of M4. One is the VDS of M2, overdrive of M2. And the last is the overdrive of M0. But I did this way because please remember, Vout reaching this minimum value is conditional upon the fact that you choose this minimum value for VB4. Okay. It is only because you have a free control over VB4, you can connect VB4 to this minimum value. I'll erase this. And only if you connect it to this minimum value, you will reach this. So that point I wanted to highlight, so that's why I did this long way. Okay. Any questions? Cool. So similarly, let's try to find the absolute maximum. So to find the maximum Vout can go to, should find maximum of VB6. So once again we can try to write it directly. So this is VB6. If VB6 keeps increasing, which transistor can go out of saturation? Why M6? For PMOS transistor, if the gate is higher, it is good. So which one can go out of saturation? Right, because if you keep increasing this, the source voltage will increase because source to gate is constant. Drain voltage for a PMOS transistor is increasing, that will be a problem. So similarly, we can try to write it directly. So here you have VDD, right? So VDD minus VDS8 minus VSG of 6, correct? That is VB6. Is this clear? VDD minus source to drain, should be source to drain, sorry. So VDD minus source to drain of M8 minus source to gate of M6, that is VB6. Okay. So if I want to have, okay, let me write it now. So this is VDD minus source to drain of M8 at a current I0 by 2 minus source to gate of M6 at a current I0 by 2. If I want to maximize this, what should happen to these two fellows? I mean, if I want to maximize this, both of them must be minimum, but you have no control over this. This is fixed. Only control is this. So what is the minimum we can go now? I mean, what is the maximum we can go then? I mean, what is the minimum source to drain you can have? That's it. Overdrive of M8 at a current I0 by 2 minus source to gate of M6 at a current I0 by 2. Okay. So if you apply this maximum voltage, let us see what is the maximum you can have for Vout. And the maximum Vout is maximum of VB6 plus mod VTH6. So I'll try to add it directly, plus mod VTH6. Okay. Sorry if it's not clear. So let me erase it so that I'll have some space. Yeah. So this plus mod VTH6. So now you see I have minus VSG plus VTH. What is that? Minus power drive voltage. So you can write it directly here. So this will be VDD. Again, now we can try to write it directly, right? Ideally, the output could have, ideally you would have wanted your output to go as high as VDD. That is not feasible. You have to drop source to drain for M8 and source to drain for M6. So that's what will happen. So you'll have VDD minus overdrive of M8 at a current I0 by 2 minus overdrive of M6 at a current of . So once again, Vout reaching this value is possible if VB6 is connected to this maximum voltage. Again, that is the reason why I again did it this way. Okay. Okay, cool. So now what I'll do is let's look back at our second candidate for telescopic cascode, which was wherever it was. Yeah. So we saw we can also do this biasing this way. So let's quickly see what will happen here. Okay. So here, as we have changed only the DC biasing, you can find the small signal gain will still be same. Nothing will get affected. Okay. So we'll only look at the DC operating point and the swing limits. So only change we have done is go and connect the gate and drains for both PMOS transistors. So let's quickly look at the bias points. So let us say apply a bias voltage VB. So what can you say about the two currents now? Again, you can argue, I mean, let's not do it again and again. It will be same as I0 by 2. Okay. Same will be, all the drain voltages on both sides will be same. So then tell me, what is this voltage? VDD minus. Again, remember that all the transistors carry a current of I0 by 2, which means their gate to source or source to gate for PMOS is fixed. So this drain voltage is also the gate voltage. So this is VDD minus source to gate of M7 or M8. So this is VDD minus source to gate of M8 at a current I0 by 2. Right? And same will be this voltage for DC operating point. This is VSG8. Now tell me what will be this voltage. Yeah, again remember that here this source voltage for M5 is fixed to this value. Once again, for M5 and M6 you need to have a particular VSG. I'll call it VSG of M6, same as M5, no change. So this will be VDD minus VSG8 at I0 by 2 minus VSG6 at I0 by 2. Fine. So here I will give finding the input common mode range as an exercise. You please work out. So what I will focus on here is just the maximum the output can go to. Okay, let's just look at that. So here if I keep increasing the out, which transistor can go out of saturation? M6. So what is the maximum the drain voltage of M6 can go to? I mean, it's a PMOS transistor. The drain for this PMOS transistor, what is the maximum limit for that? Yeah, it is the gate voltage plus threshold. Fine. What is the gate voltage for M6? Huh? What is the gate voltage for M6? VDD, whatever you have written here, right? So this is essentially the gate voltage of M6 plus mod VTH6. Fine. This is VG6 if it is not clear. And this we have already computed. This is VDD minus VSG8 at a current I0 by 2 minus VSG6 at a current I0 by 2. That is the gate voltage. The drain can at the max go one threshold above it. So once again you see this term. What is that? It's a overdrive voltage. So I will write it like this: VDD minus VSG of 8 at I0 by 2 minus V overdrive of 6 at I0 by 2. Okay. So this in turn I can write it like this. This is overdrive of M8. I mean, if I write it like this, what should be the change I make? That is, I am replacing VSG as V overdrive 8. So what should be the term I add or subtract? Minus VTH. Okay, mod VTH 8 L3. Okay. Okay. And now it's a time to compare the result we got with the other circuit. Now with the other circuit, the maximum Vout was VDD minus the overdrive of M8 minus overdrive of M6. Now let's look at the same thing here. What do we have here? VDD minus overdrive of M8 minus overdrive of M6 minus a threshold voltage. So which of the two circuits is better now in terms of the output swing? The earlier one. Okay. So that's the point I wanted to make. So let me actually draw the two. So this is the second variant. This is the first variant. Okay. So here this one can go, the maximum output can go here is higher than what you can get here. Right? So please have that in mind, because the reason this is better is, I mean, the reason the output can swing higher is, as we saw earlier, the output reaching the maximum depends on what is the gate voltage, right? And in this circuit, you had full freedom to connect the gate to whatever voltage you want. So which means you could connect this gate to this maximum voltage to make the output go to the maximum value. Whereas here, the gate voltage here is set to some other voltage here, which is not convenient for output to reach the maximum. Okay. So because please have that in mind, because it might be very tempting to just look at the circuit on the right side and conclude that the maximum the output can go is VDD minus overdrive of 8 minus overdrive of M6. That might be very tempting to say, right? But that is not the case, because fundamental limitation of the swing limit is coming from the gate and drains. Okay, so you always look for the gate voltage, and then you see what is the limit. I mean, if the gate is free to connect to whatever you want like this, then you can say. So please have that in mind. Yeah.
In the first thing that we argue that V out and that the drain of M5 is same, right? And also that drain of M5 is connected to gate of M7.
Correct.
So isn't that that drain is fixed like VDD minus ESD7?
That is at the operating point.
Operating point, right?
Correct. Operating point is fixed, but when we are talking about the output swings, the assumption is we are putting this in negative feedback. Let us say you put in negative feedback, then the voltage will be different from the operating point. Now the operating point is set by what bias voltages you use, and that is why you are trying to see what is the maximum you can have at the Vout, minimum you can have at the Vout. Is that clear? Yeah.
Currents won't be same in both of the left part and right
Correct.
part.
That's true. The moment you have, the moment you have signal swings here, right? Then you cannot say that.
So all the everything we are using VSG6 at I0 by 2. So that won't be.
Yeah, I mean that's the idea, right? See, it's the idea is, I mean, if you want to do the exact calculation, it's going to be very messy, right? But this gives you a good starting point. That's all, right? And the other thing is, we kind of can make an assumption that the dependence of drain voltage on the drain current is not significant. It mainly depends on VGS, and for sure we know the VGS is same even if you put in negative feedback. So that way the calculations will still be fine. Okay, so again, this is something new. This is yeah, these two are two different things. So differentiate them. You have to give some name, and the name that is given is this. So this portion is often called the high swing cascode current mirror. It's a matter of fact naming, high swing cascode current mirror. Because at the heart of it, both of them are current mirrors, right? And you are having cascode current sources, and the cascode current sources are getting mirrored. But here, as we know, the output swings is higher, so obviously it's called this. Okay. So any other questions on today? Okay. So then I'll stop here. Yes. Sorry. This is just you can call. This is a normal cascode. The idea is if you name one, maybe you don't have to name the other. I don't know. Yeah. So thanks. So meet you tomorrow.